So from a purely practical point of view, we have now introduced the schemes, this new fancy language, but we already did a whole course on varieties and pre-varieties. And we have a pretty good theory now of these things. We have many examples. We know a lot of their properties. And the question is, do we have to, if we want to work in a language of schemes, do we have to do everything again now in this new language? And the answer is no. So somehow there's a way to import basically all of this theory of pre-varieties into this language of schemes. In other words, for any pre-variety X, we get a canonical scheme X scheme. And we have already seen this, for example, for affine varieties. There we just said, well, if X is an affine variety, then take its coordinate ring and then take the associated spectrum. And we have already seen that the spectrum is basically a very fancy extension of this original variety that we started with. And so, but this was all in the affine setting. And so how can we now take an arbitrary pre-variety and get this scheme out? And of course, the first idea maybe is, well, this pre-variety has a cover by affine varieties by definition. And so we convert all of these into affine schemes, and this should give us a cover of this X scheme by affine schemes. And this works. And so let's go through this idea. This first idea, basically just gluing this thing. So as I said, X pre-variety, so it's this affine cover by affine varieties. And then if you want to glue them, we already know we need to start identifying them. So on these overlaps, these intersections of these affine varieties will not necessarily be affine. So for a variety, they are, but for pre-varieties, they wouldn't necessarily be. But we can take this overlap and cover it by further affine varieties. And then, well, how can we get the scheme representation of X? Well, you just take these affine varieties, their coordinate rings, then the spectrum gives you affine schemes. So for each of these red things, you get an affine scheme, and then you glue them together, and how you glue them together is exactly along the affine schemes for these blue parts covering the overlaps. And the good thing is that we know exactly, because there's a restriction map from the coordinate ring of ui to the coordinate ring of these blue things. And then turning it around via spec, we get maps from all of these things into these. These turn out to be open subschemes, and then in principle, we can try to glue this together. So this works. This gives us the desired scheme, and many properties can be checked like this. The problem, as always with these gluing constructions, is that it's not clear a priori that the result will be independent of what affine covers we chose here, and it's just a bit tricky to then prove many nice things here. So the second idea, how we get this scheme, is that in fact it's not so terrible to just write it down, because I mean, scheme is a topological space, a sheaf of rings, and we can just do it. And this is the following proposition. So pre-varieties at schemes. So we start with X, a pre-variety over an algebraically closed field. That's the setting of the entire first part of the course. And then we write down what the scheme is. So X scheme as a set, it will just have a single point, which we denote by Y in bracket, for Y any irreducible closed subset of the pre-variety X. This is the scheme on the level of sets. Then on the level of topology, there's a very tight connection, because for any Z inside X, a closed subset, you get a curly Z inside X scheme, and it's just these points Y such that this irreducible closed subset Y of X is actually contained in the closed subset Z. So here, any closed subset of X gives a closed subset of X scheme. And you just say the topology is, well, these are exactly all the closed subsets. So this tells you what the topology on X scheme is. And then finally, we need to define the structure sheaf. And the good thing is, so let's say U inside X is open with complement Z. Then by the definition of this topology, this curly U, which is X scheme minus the curly Z, this is an open subset of X scheme, right? Because curly Z is a closed subset. And so this thing is an open subset. And in fact, these are exactly all the open subsets because these are exactly all the closed subsets. So any open subset of the scheme actually comes from an open subset of X, like this. And then you just declare that the ring of functions on the curly U is exactly the ring of functions on the non-curly U. And similarly, so this defines it on any open set, and then you need the restriction operation to get a sheaf, and you just take exactly the same restriction operation from here. And that's it. That's the three things that we need to specify, and then this pair, this topological space with this sheaf of rings turns out to be actually a sheaf of locally ringed space, and then this is a scheme. That's the first claim. And this is the scheme representation of this pre-variety here. And then the second one, so now we know about the individual objects and then about morphisms. Whenever you have a morphism from X to Y, then you get a morphism from their scheme versions in the same way. And so this already shows how all the examples that we had before become now examples of schemes, or the morphisms that we know how to construct between them, examples of morphisms of schemes. So this imports a lot of the theory. Also, I mean, I think I don't write this down, but for example, from this representation of the topology, then when you look at something like the dimension of X, and this is the longest chain of irreducible closed subsets here, well, because the closed subsets exactly correspond to closed subsets on the other side, the dimension of this X scheme is exactly the same as the dimension of X, for example. That's just a 3-line exercise. And so basically the entire theory that we know with just a few adaptations immediately transfers to this language of schemes. Okay. And so for this proposition, we're not going to give the full proof because it involves a lot of, I mean, checking all of these properties. Of course, there's a very long laundry list of things which you need to check. So for example, things like this is still a topology. And that's basically just kind of standard arguments. Any property of this set of closed sets follows from the corresponding property of the Zariski topology on X. So we're just kind of going through the highlights of this proof. And the proof idea for this first part is basically that this here is now a nice global description of something. And I mean, somehow basically to check that this here is a sheaf of rings, for example, this is just standard nonsense. And so what you really need to check now is that locally this here looks, this has a cover by affine schemes. And then the idea from the first part comes in because now we can just see where to get this affine cover. And so the idea there was that, well, whenever you have ui inside X, the rational pre-variety, if this is an open affine variety, then we want to construct a map from, we want to start with spec of a ui, and basically want to construct the map. Let me see. We want to have a map here from the spec a of ui to X scheme. this is where we want to land, because then what we will then check is that if X has this affine or this open cover by affine varieties UI, then the X scheme will have this open cover. So this will give open cover of X schemes by the spectra, and this is what we need to prove in order to prove that it's a scheme. And so we need to define what this cover here is. And so, for example, we need to understand what it is on the level of sets. And so we start with P inside spec of the spectrum. So P is a prime ideal inside A of UI. But then we know the prime ideals of the coordinate ring correspond to Y inside UI irreducible closed subset. This is one of the first things that we showed about affine varieties. And so we have an irreducible closed subset of UI, of this open thing. And then we need to get, in X scheme, the elements are these irreducible closed subsets of X, of all of X. But what we can just do is we can take the closure inside X, and the closure of something irreducible is irreducible. It's also closed because of the closure. So we get an irreducible closed subset of X. And from this, its class, like this here, is an element of this X scheme. Right? And so this means we start with a point in this spectrum, we get a point in X scheme. So this defines on the level of sets this map here. And then what you check is this works well with the topologies. And so in fact, from this cover, the cluing recipe that we discussed before gives X scheme as a topological space. So this shows then, once you check this, this shows that this is an open cover on the level of topological things, and you can get this by gluing. And then the only thing you need to check is that this is also an open cover on the level of ring spaces. So somehow what you need to finish the proof is to compare these rings. So somehow what you then check is that OX of U is isomorphic to O X scheme of this curly U. And to do that, you first check it on these affine varieties. And then for the part B, this kind of formorphisms X going to Y like this. Well, now you want to get a morphism between these X from X scheme to Y scheme, and I mean, you can again write down what this morphism does essentially on the level of points, for example, and then construct it like this. But in the end, you need to show that this is a morphism of locally ringed spaces. And to do that, you want to reduce it to basically a morphism from some cover of X by affine from some cover of X scheme by affine schemes to a cover of Y scheme by affine schemes. And how you do it is you first start, when you want to construct these compatible covers, you always must start with the target. So you cover cover Y by affine subsets V, and then cover this pre-image by affine subsets U, and then you get a map from U to V, and so the pullback gives you a map from OY of V to OX of U, and then now we have a map of rings, and then we're in business that then we can show that the corresponding maps. So we have now the spec of OXU. Now we get a map of the spectra in the opposite direction. Like this. And this here, this sits inside X scheme, right? Because we got X scheme, we found this kind of cover. And similarly, we have here, this sits inside Y scheme. And then you show that these things here glue together. So there exists this F scheme between them. So show that these glue together. And once you know that, well, then you know this here is a map of local ring spaces. This we checked that somehow if you have a map of rings, then the map of spectra in the opposite direction is a map of local ring spaces. And then this shows it automatically for this glued together thing here. And then this is exactly what we claimed, that starting from a morphism here, you get the morphism of the schemes here. And so I know this was a bit sketchy, but going through all of the details, I mean, would be a very long list, and many of the arguments are basically just standard. So I encourage you to try to fill in some of the things here. Okay, and so this was all a bit abstract. So let's conclude the video by some concrete example. Namely, I mean, we already know how to convert affine varieties into affine schemes. So let's start with basically the simplest possible non-affine variety. And this would be P1. And so we just ask, what is P1 scheme? And we'll also keep in mind these two approaches that we had before. So let's actually start with the first idea. Namely, well, P1 has this cover by two copies of A1, which are these charts U0 and U1. And A1 has coordinate ring, just a polynomial ring and one variable. And so what the recipe above tells us is that we should take the spectrum of this ring, another spectrum of this ring, and then glue them together along the overlap. All right, so this would be the first idea. And so we have this copy here, this copy, and how they fit together. Well, we take the complement of 0 in one copy, the complement of 0 in the other copy, and then the map of rings between them was this ring which was this map which sends W to 1 over X. So somehow you glue basically something here to the sorry, I guess this should be, yeah, exactly. So this is a generator of this, and you send this generator to this generator 1 over X on this side. Okay. And then what does this do on the level? So we understand pretty well what it does on the level of varieties. So what does it do on the level of schemes? Well, we have that the schemes compared to the A1 basically look the same. They have 1 point for each element of A1, and then they have this extra point, this kind of generic point, corresponding to the 0 ideal. And similarly on the other side. And then what happens is that this here sends, for example, this closed point 2 corresponding to the ideal X minus 2 on this side. this sends it to this point 1/2 on the other side. Because basically it must do the same thing on the closed points that we already know. And then this 3 gets sent to 1/3. And kind of, if you want to check it purely on the level of algebra, you can see that the preimage of this ideal generated by x minus 2 here in this thing is exactly w minus 1/2. So the closed points here, which are the closed points except for the 0 point, they get identified as we expect. And then on the level of rings, I mean, this is an isomorphism from this ring to this ring. In particular, the preimage of the 0 ideal on one side is the 0 ideal on the other side. This shows that these generic points also get glued together. And this is all kind of gluing. If you glue this scheme and this scheme along these open parts, so these get identified. The only things which don't get identified are these two 0 points. And so if you then write down what space you get, well, you get a space which has 1 point for each of these closed points away from the zeros. So these are these blue points here. It also has 1 point, which is the glued together thing from this generic point and this generic point. And then it has these 2 special points, the red one and the pink one, like this, which become kind of the 0 and the infinity point of this P1. But then, so this was all in this language of the first idea, just gluing together affine schemes. But then you can also look at the recipe which we gave, so P1 scheme. So what do you expect in P1 scheme? It should have 1 point for each irreducible closed subset of P1. But P1 is one-dimensional, so it doesn't have that many irreducible closed subsets. It has 1 for each closed point. And these are exactly the closed points of P1. And then it has 1 point for the full subset, which is P1. And you can check these recipes exactly line up, because somehow this is the image of these generic points, and all the closed points are also accounted for from this gluing construction. So, I mean, meditating a bit over this exactly tells you that these 2 ideas of getting the scheme representation give the same answer in this case. Okay, so this was at least a small example of this thing. And to conclude, let me also say for kind of category fans, so what we described above, this recipe, which takes X and produces this X scheme, and which takes this morphism here and produces this morphisms between the schemes, this is exactly a functor from the category of prevarieties, let's say prevarieties over K, to the category of schemes. And this is not just some functor. I mean, this just requires checking that, for example, if you have the composition of 2 things, you get the composition of the things here. But it's actually what is called a fully faithful functor. This tells you that this map on the morphisms is actually bijection from the morphisms here to the morphisms between the schemes. This tells you that that for these new scheme objects, any possible morphism from this to here actually comes from the morphism of the prevarieties. And that's reassuring, because it means if we understand these morphisms here completely, then we understand these. And then such a fully faithful functor is then actually often called a full subcategory. And you should basically think of this category of prevarieties sitting inside the category of schemes. And that is that is kind of reassuring, because it tells you that the prevarieties, basically anything that you can understand about them, you can also kind of recover in this language of schemes. Okay, so yes, that was everything I want to say about how to import this. And now we're going to make, in particular this year, we're going to make it a bit more precise in the coming videos, and show how do you recognize, if you are given a scheme, how do you recognize whether it sits inside this subcategory here? How do you recognize the pre-varieties inside these schemes? So that's the next thing.